Good morning, everyone. My name is Harsha Nippani. I'm a solutions architect at AWS. Been with AWS for 5 years. In this session, we'll be diving deep into, this is a 200-level session for folks who are familiar with our compute offerings. We will touch on some of the aspects of compute options that you have on AWS, and then we will dive deep into some of those, exposing you to some patterns on deployment, and then we'll talk about specific use cases. So before I get started here, just to give you some piece of information, we're doing a series of at-scale presentations today. This is the first of the sessions. After compute, we will be talking about security at scale, and we'll be talking about CI/CD at scale, and management at scale. So if you're interested, please attend those sessions, and it'll give you a holistic view about all the options you have in terms of deployment. All right, for compute at scale, we have, in this session, I will be talking about 3 different compute patterns on AWS, EC2 at scale, containers at scale, serverless at scale, and then deployment patterns within those. All right, let's start with EC2. 5 years ago, we had one service that is focused on compute. It was EC2. We still have EC2. These are the virtual machines that you deploy on AWS. For folks who are familiar with virtualization, a lot of transformation has been going on in the data center world, where migrations from mainframe to open systems, from open systems on bare metal to data center virtualization through hypervisors, which is VMware-based mostly, or Hyper-V, and then eventually cloud-based virtualization, which is EC2. In EC2, you have multiple options in terms of deployment. It's basically either Linux-based virtualization or Windows-based, and we provided a lot of options in terms of deployment. So to give you a perspective of how we evolved over time, EC2 instances started with just 3 instance families and instance types. And over the past few years, we now have about 70 instance types and about, I think it started off with 1 instance family, and we scaled to 12 instance families. All right. So compute services is at the heart of transformation journey for a lot of customers. It's extremely important to understand the differences in terms of compute patterns on AWS. One is you have the traditional VM model, which is EC2. Then you have the container model, which is basically ECS, Elastic Container Service. And then you have the serverless model, which is Lambda. A lot of customers have leveraged all 3 different patterns. These are not one-size-fits-all based on your workload necessities, whether it's a stateful application or stateless application. If you have long processing, batch jobs type requirements, or you want to do distributed computing, HPC workloads, based on different patterns, different application workloads, different characteristics of your application, you may pick and choose different types of compute pattern that suits your application. And finally, starting from EC2, the journey has evolved, and now this is the complete AWS compute business as of today. To the left of you, you can see the EC2 instance, and it's all the characteristics that make up the instance operations, including AMIs, the Amazon Machine Image. And then you have the EC2s and the types of EC2s in terms of spot instances or on-demand or reserved instances. And then you have a complete suite of container-based services, including ECS, which is Elastic Container Service, EKS for Kubernetes, and then you have ECR, the container registry. And then moving into the networking, we made a lot of advances in terms of networking within the EC2 fabric. You have the VPC constructs, you have the NAT gateway, VPC peering, and then going into the serverless model, before we hit the serverless model, there is Beanstalk, which is basically another container-based service with which you can easily deploy onto AWS. And finally, you have load balancers that you can take advantage of. If you're familiar with on-premise load balancers where you are using F5s, for example, a lot of customers use F5 GTMs and F5 LTMs for routing both globally and locally into a data center. So you could do easily, you can extend that functionality using ELBs. You have 2 sets of load balancers available to route your traffic to the compute engine, either network load balancers at the layer 4, or if you are routing to layer 7, which is application load balancer, ALB, or you still have option for the standard classic ALB. So regardless of, what I'm trying to explain here is you have a breadth of options on Amazon, on the AWS platform to extend your workload necessities and essentially target specifically deploy a particular stack, right? Now, for this session, I'm gonna be focusing on the 3 areas, the compute, the containers, and the serverless. Just to level set here, EC2 is our virtual machine space service suited for big data workloads to migrating your enterprise applications to AWS. And then you have containers-based solution. Basically, if you are leveraging microservices on AWS, you would take advantage of either Beanstalk or a suite of ECS, EKS deployments. And then you have another implementation is Batch that's also based on containers. Batch is leveraged by financial services industry, life sciences. Again, this is another extension to the container model. And then you have function as a service through AWS Lambda. This is event-driven programming for customers who don't want to maintain servers to execute who still require small amounts of compute on demand and not have to maintain server infrastructure. AWS Lambda, which is based on event-driven programming, is a very good choice. All right, let's dive deep into EC2. At AWS, innovation is at the heart of every single service and the offerings and the products and features. The same thing applies to EC2. We have started in 2006 onwards. It has grown in scale, continuously innovating in terms of offerings that we have, from general purpose instances that we launched to compute optimized and IO optimized and storage optimized. The reason why we developed so many different instance families is based on the customer feedback like you, who have asked us to purpose-build specific virtual machines for specific tasks. Why is that important? Because not all workloads are of the same type. You have CPU-based workloads. You may have graphics rendering. You may be doing video streaming, and you need specific computation that is suitable for that workload. So for that, you would use typically a GPU-based instance. So that's the evolution of CPU-based virtual machines to GPU-based virtual machines. And then there is large-scale financial applications that also require additional hardware acceleration. And we provide hardware acceleration through FPGA instances. So when you see a wide suite of VM options on AWS, the reason is different workload characteristics and different types of CPU and the processors. And then finally, we launched the EC2 bare metal at re:Invent, and we're going to be talking about that as well. So before I explain why we have so many instance types, it's extremely important to understand the evolution on our side, why we have developed EC2 instances, and why should you care? So this slide I borrowed from a gentleman, Brendan Gregg. He's a performance architect at Netflix. He put together the chart. The reason why this is extremely important to understand is the evolution of EC2 over time. At the top level, you can see the Zen PV, like line item number 2. You can see these are the PV driver-based virtual machines. Why is it important for you to understand this is a direct correlation between the driver set and the chipset that we have that's powering the EC2 has a direct correlation to the performance characteristics that you can gain out of virtual machines. So in this case, we started off with PV drivers. These are para-virtual drivers. Basically, what happens is if your operating system is making hypercalls, if it wants to talk to a hardware device like a NIC card or a storage device, what happens is those hypercalls get addressed at the driver domain layer, which is basically a hypervisor layer. And from hypervisor, those calls get delivered to the hardware layer. So there is always a latency aspect when you are rerouting those requests, those hypercalls, from operating system to hypervisor, and from hypervisor to the bare metal. So the PV drivers were doing OK in terms of handling those interrupts, right? But there was an amount of latency, and the latency could be anywhere between 10% to 50% of hardware resources that is consumed by the PV fabric. And then over time, we launched HVM-based drivers. HVM is a hardware virtual machine. Basically, with the advent of specialized microchips that we have developed, what we could do is to start offloading, instead of routing your request to the hypervisor domain, we started offloading some of those requests directly to the bare metal. Why is that important for you? Because networking has always been a bottleneck for virtual machines. And by offloading networking to a specialized network acceleration card that is directly attached to the box, your virtual machine can talk directly to, based on specialized drivers, they can directly talk to the hardware devices, and with which you will get better performance, lower jitter, and that is how we are powering HPC workloads. And over time, in 2013, we have introduced the line item number 5 here. The SRIOV, single root I/O virtualization, is the technology that we have introduced through which we offloaded that networking network acceleration. So you may be familiar, some of you may be familiar, that there is something called enhanced networking. So when you enable enhanced networking on the EC2 instances, you are basically telling the operating system to leverage that direct connection to the virtualized hardware NIC card. So after solving that bottleneck with networking, we targeted storage. So storage is another area where there is latency when you're doing I/O operations against your EBS volumes. So we extended the exact same framework to storage layer, and we solved that problem by introducing the C3 type instances, essentially taking advantage of SRIOV to the storage layer. So we solved the networking bottleneck, we solved the storage bottleneck, and then we introduced at re:Invent last year C5 instances and M5 instances. These are completely based on a new hypervisor module that we have developed. It's no longer based on Xen hypervisor. This is KVM core kernel modules that we have leveraged, and we removed the ancillary functions like KMU and just created a very lightweight hypervisor so that there is no concept of DOM0. DOM0 is also referred to as the domain driver. So all your hypercalls, starting from C5 to M5 and the latest generation servers, which are based on the Nitro system, offloads directly to the hardware. So it is as good as running your virtual machine that has direct access to a bare metal instance. So there is no real, based on the performance metrics that was measured by Brendan Gregg at Netflix, what he came up with is, based on the numbers he calculated, it is less than 1% or less than 2% overhead using the Nitro system versus Xen, which still had up to 40% overhead in terms of managing hypercalls. So that's why this chart is important for you. Here is just a quick overview of why this split driver domain model is important. So if your guest operating system, this is where your virtual machine is running an application at layer 7. When your layer 7 makes a network connection call, it goes through a network socket connection, and the front-end driver on the operating system, the number 2 here, That's the one that connects to the backend driver, which is your hypervisor domain. And that hypervisor domain, the DOM0, interprets and those hypercalls and talks to the network device. So this was the old school of implementation. And then what we did is with this RIOV, we offloaded the driver domain. And this is how now the hypercalls are handled. So the advantage of this is, these are all, by the way, is HVM-based AMIs. So it is extremely important for you to understand PV AMIs and HVM AMIs are two different methods through which you can launch EC2 instances. We strongly encourage HVM-based AMIs. Why is it important? Because PV drivers do not support hardware acceleration. They don't, that's the disadvantage of PV. So on the HVM side, you can take advantage of hardware acceleration, meaning these hardware devices, like the networking chip, the storage, all these are virtualized and can be implemented through specialized drivers at the OS level so that you can get very high performance. So the themes are, again, unless you have a specific necessity to either have an application that requires access to bare metal or due to licensing needs, you have to have your application running on bare metal. From a performance perspective, there is no real reason why you have to run on bare metal. We have developed so many efficiencies into the system that your Nitro-based virtual machines can deliver near metal performance by doing the device pass-through. So that's all CPU. Also, it's important to understand the landscape here. There is GPU-based and FPGA-based instances also, like I mentioned earlier. GPU, again, enabling high degree of parallelism. You still have sequential instruction set passed to your CPU level. Similar to CPU-based instances, GPU also have sequential instruction set passed. However, you have advantage of doing, again, their GPU has thousands of cores. There is a degree of parallelism that you can take advantage of. This is the reason why graphics-based workloads are recommended to be run on GPU-based instances. And same thing for, to extend it even further, the field programmable gate array, the FPGA-based instances are massively parallel. They're very flexible. There is no fixed instruction set at the chip level. It's field programmable. So that means it gives you, again, your developers much more flexibility in terms of leveraging FPGA and its functionality. In summary, again, use more modern operating systems that can take advantage of these hardware acceleration. It's extremely important to understand the drivers. Again, I recommend you to leverage HVM-based AMIs for your workloads on AWS, and definitely leverage enhanced networking for low latency, low jitter, high performant network throughput. And it's always important to also do profiling your applications. So now extending your EC2. So once you pick your hypervisor, your AMI and the EC2 instances, the next thing is operating at scale is obviously meaning you are automating the functionality where you're getting on-demand instance types or on-demand compute options. And the best way to implement that at scale is enabling auto scaling at the EC2 layer. A lot of enterprise customers have done this seamlessly. The idea being you can scale based on the demand spikes. One pattern for auto scaling is replacing unhealthy instance types. This is also called fleet management. In a fleet management scenario, what you're doing is you have a set of web servers that are behind a load balancer. Say the hypervisor, the EC2 hypervisor dies because of a hardware problem or whatever the problem is, and then your EC2 instance is no longer routable or it cannot ARP to the network. When it cannot ARP to the network, obviously it cannot receive traffic. What happens then is with EC2 auto scaling features, it does a health check on your behalf. This is all automated. And if there is an unhealthy instance or impaired instance, auto scaling group can automatically replace, first of all, shut down the instance, the impaired instance, and replace it with a healthy instance, and register it back to the ELB. This gives you that ability to have fleet management in an automated fashion. And then the second pattern is dynamic scaling. This is also extremely important for customers. One classic example I can think of is the healthcare.gov rollout. It made press coverage, a lot of issues during the rollout. One was the registration. During the registration process itself, the system was down, and then once the registration was done, again, there was another event. So if you look into this type of events, it's extremely important to understand the crux of the problem there was, again, the inability to scale because of unexpected spike in the workload, right? To handle situations like that, typically what customers would do is you are architecting for peak workload, but then if you're architecting for peak workload, then there are phases where the workload is not really operating at peak. That means your hardware is sitting idle. To resolve that in a more TCO, with a better TCO, better return on investment, the option is to leverage auto scaling with the dynamic scaling option. There are multiple ways you can do this. You could do based on CPU. You can based on a specific time window, meaning scale up in the morning and scale down in the scale back in the evening. So something like that. Take advantage of a dynamic scaling option. Again, just to recap, at scale, EC2 auto scaling benefits. There are three important points here. Improve fault tolerance. This is based on fleet management. Increase application availability. This is making sure you have the right computing capacity available for your application as the requirements are. And then lower costs. How can you lower costs? Based on, again, scaling only to meet your actual demand, not architecting for peak, right? All right, just a quick summary here. Also an example on how auto scaling works. In the first command set, you can see the way this is actually implemented is you have to first create a launch configuration on auto scaling. You will be defining in the launch configuration your SSH key pair, your instance ID in this case, security groups, and then you would define what instance type you want as part of your auto scaling group, and then basically associate with that with a public IP address if you need to. So once you have your launch configuration, the next step is to create your auto scaling policy. And when you're creating auto scaling group, all you are doing is pass that parameter, what the launch configuration that you have created in the earlier step, and telling auto scaling group to leverage that and register any new instances that were launched as part of auto scaling with a load balancer. So that way it's all automated. It's pretty straightforward. It doesn't take a lot of coding for this, and you can automate this and include this in your provisioning process, be it CloudFormation or any other provisioning process that you use, as long as you are compatible with APIs. All right, just to summarize another topic that we already covered, the EC2 Nitro system. We really deeply care about continuous innovation, continuous improvement on our platform, all compute platforms. So C5, M5 give you, these are the two new instance types that are based on the new Nitro system. I already explained to you what the hardware acceleration mean and how the chipset offloading to the network card or the storage, NVMe storage, takes advantage of the hardware acceleration. The bottom line for these instances is there's anywhere between 25 to 50% price for performance improvement based on the previous instance family, which was Zen-based. We have also extended this to this innovation into other instance classes. This is the storage optimized instance type. You also have this concept of ENA. Typically with elastic network interface, you get up to 10 gigabits per second throughput, and then with the ENA introduction of ENA, you can get up to 25 Gbps if you're running in a aggregated in a placement group. So extremely powerful, and also a lot of local storage available. And bare metal, We announced this at re:Invent. There are two major implementations for bare metal. The one is, again, like I mentioned earlier, the i3 instances. I think this is now generally available, i3 instances or the metal instances. If you have specific requirements to run on bare metal, your application stack, you can absolutely do that on EC2 bare metal. But the most important implementation has been targeted for hybrid workloads. A lot of my customers, the customers I've interacted with, have some form of virtualization already on-prem. Most likely it is VMware or some other similar technology. So for customers who have VMware and want to extend their VMware functionality into AWS, because they've already made significant IT investments and they want to extend that functionality and get the scaling and integration into AWS, in a use case like that, hybrid implementation is the obvious choice for customers because they just cannot lift and shift. They want to extend the framework in a more seamless pattern. For those types of workloads, we have launched at re:Invent VMware Cloud on AWS. There are a couple of sessions that are going dive deep into this. If you're interested, do attend those sessions too. But essentially, the crux of it is VMware on AWS is an implementation, is a partnership with VMware in providing a solution for customers who want to extend their VMware framework into AWS. And under the covers, VMware stack is taking advantage of the bare metal instances that we have launched. One question I often get asked about from customers is, what if I'm running VMware on top of bare metal? Are you all doing nested virtualization, meaning VMware virtualization and then under the covers EC2? No, we're not doing nested virtualization. It is only ESXi, right? And we're not doing another layer of hypervisor. These are bare metal servers directly available to ESX. And VMware is managing those servers, meaning the ESX layer, and we are managing the underlying bare metal. So there is no latency or dual nested virtualization that will affect your performance. The very good advantage for this is you can extend your VMware SDDC onto AWS and seamlessly migrate. You could literally do a vMotion from your, say, if you are in the vSphere interface, you can take your virtual machine that is running on VMware and do vMotion into the AWS side. So that way you can actually start scaling better. And if you are running into a scaling issue and you need additional compute capacity, you could do that. Going into F1 instances, this is the FPGA type instances that we were talking about. And the reason why I wanted to highlight this is during one of the POCs, they set a new world record for fastest analysis through FPGA instances, getting 100 genomes processed in a record time. That's the kind of, the advantage over leveraging these types of instances on AWS is not only it gives you the ability to experiment, it also gives you ability to fail fast. So try experimenting. And if something is not working, you can quickly iterate and also adjust your workload requirements based on the output that you're getting, and you can monitor through CloudWatch, integrate that, and be more productive. Next is the G3 instances. Again, there is already a GPU-based instances. So why did we introduce G3? This is even more highly highly graphics-driven processing workloads that the customers asked us to develop as another set of functionality. So we launched the G3 instances. In this case, Halliburton leveraged the G3 to do seismic exploration. And a lot of details here in terms of 3D rendering. They needed specialized hardware to do that type of high-level 3D rendering, and we launched G3 instances for that exact workload characteristic. Another evolution, this is the P3 instance types. Again, a lot of customers have been asking about, hey, what do I do with respect to AI and ML type workloads? Is there any specialized EC2 instances for that? We have, again, just imagine the scale of the data, right? I mean, there is 1.2 trillion photos taken in 2017. That's massive scale, right? It roughly equates to about 5 terabytes per person. And when you're doing a lot of computations that are specifically for machine learning and artificial intelligence, the P3 family is essentially targeted for that type of workload. It gives you faster machine learning training models, and also the P3 instances provides up to 1 petaflop of compute performance, extremely performant. All right, the second pattern here, containers. Why is containers important? Does anyone is familiar, raise of hands, aware of containers? And OK, great. Back in the day, does anyone know Solaris containers? So Solaris containers, again, I think this was more than 10 years ago. That was when I was working as a system administrator. Not just, I mean, even before massive adoption of Docker containers, one common model was we had a large box. We wanted to virtualize multiple operating systems on top of the box, right, and give a segmentation, a piece of the hardware dedicated to that box, right? So Solaris 10 provided that option for containers. That was fantastic. You had 2 options, either sparse root or whole root zones. Those zones had access to the hardware devices, but the problem was it was still multiple operating systems under the covers, right? You still have a operating system, and you're running, you have the physical bare metal. On top of that, you have a virtual machine that's running an instance of the operating system. Docker took that concept of containers, and they leveraged it, and they made it 100 times better through container technology. And a lot of customers have jumped onto that bandwagon. Why is that important? Because not only it gives you a faster DevOps model, but also it gives you ability to host, basically leverage a lot more applications using the same set of hardware, but also give you segmented space so that you're not crisscrossing. So based on that feedback that we have received from customers, that they're already running Docker containers on top of AWS, on top of EC2, based on the feature requests, based on the customer feedback, we have launched 2 services, ECS and EKS. What are these? These are basically the control plane for containers. Control plane meaning instead of you managing every single aspect of not only provisioning the hardware, but also managing the traffic flow between the containers. It is extremely painful to manage this yourself because there is a lot of elements in terms of managing a huge cluster of containers on top of virtual machines. So we created a new control plane, and we gave access to the control plane to you, for you to leverage. So your interactions with containers on AWS is through that control plane. And what we are doing behind the scenes is the orchestration between the containers is offloaded to Amazon so that you can focus on deploying your applications into containers. So there are 2 control plane options. One is ECS, Elastic Container Service. Typically, most of the Docker deployments are leveraging ECS. And then for folks who are used to Kubernetes, this is Google-based Kubernetes, and they want to extend that Kubernetes functionality into AWS, we launched EKS. EKS, essentially, the advantage of EKS is if you have Kubernetes, we are managing the master nodes across 3 availability zones so that you have high resiliency, high durability in terms of your functionality, and also availability, right? Uptime. So you don't have to do your own HA clustering on your own. And then we launched Fargate. I will touch on each of those a little bit. Benefits of containers over virtual machines is basically environmental consistency, developer productivity. Why? Because if you think about it, if you are making code changes, if you are having a monolithic application, and if you have tens and hundreds of subsystems that make up the monolithic application, it's very difficult to make configuration changes without breaking anything, right? So to solve that problem, instead of having a monolithic application, containers-based, services-based deployment model has been very popular with the developers. And to help you with that, containers give you the flexibility to quickly, iteratively update a service through a microservices strategy. And if something is not working out, you can do, again, one of my peers, Yuri, will be talking about CI/CD, through which you can actually do dynamic updates on the fly. And if in case you're having any issues with a specific service, you can quickly, in a blue-green deployment model, you can quickly revert back to previous version. A lot of customers are using containers or AWS. This is just a small segment I'm showcasing here. But what I'm trying to highlight here is this is prime time. This is enterprise ready, enterprise grade. A lot of customers are already taking advantage of containers on AWS. Of course, the deployment models are different, but essentially leveraging ECS and EKS. And the advantage is offload the heavy lifting of managing the clusters and the entire provisioning process to Amazon, and you can focus on providing functionality for your users or for your end users. So quick overview about ECS here. Run containers securely inside your VPC. This is a great add-on. You have your ENIs attached in the VPC, so you don't have to publicly expose your containers. You can extend your data center functionality into AWS with, say, most of the customers that I interacted with have some form of VPN connectivity or have a direct connect from data center into AWS, and then have a VPN overlay to encrypt the traffic end to end. And once you have that type of functionality, what you can do is you could do microservices deployment on AWS and expose your internal users to hit that microservices inside your VPC. Why is that an important factor? Because as agencies are looking at leveraging cloud computing, InfoSec will often have a lot of questions about, am I inadvertently exposing my traffic or my sensitive data to the internet? You don't want to do that, so to extend that functionality into AWS, we provide VPC, the construct of VPC through which you can create private subnets, deploy all your workloads into private subnets. So these are not routable through the internet. These are RFC 1918 space, so it's all internal. Only your routers can route to that specific segment. And tight integration with native AWS services. That's also very good, very important aspect. So one key differentiator I want you to understand, a lot of questions about what is EKS, where would I use ECS and EKS, what is the differences between the two, is from an EKS perspective, there is traffic will hit the load balancer. The load balancer will send the traffic to the nodes. Nodes are the EC2 instances that are behind the scenes. And there is an agent running on the nodes. That agent will receive the traffic and then send it to your pods in Kubernetes. So that is pattern one, EKS. Pattern two, exact same thing. Users will hit instead of ELB, they will hit ALB, Application Load Balancer, the layer 7. And there is no forwarding to an agent. ALB will directly send it to your task nodes. So ECS implementation is skipping one step. So that's a little bit more tighter integration on AWS side, a little bit more functionality, more performant, and a bigger advantage in terms of ECS. I'm not trying to promote ECS or EKS, but what I'm trying to give you is a good understanding. But if you have Kubernetes implementation, the advantage of EKS is if you already have invested into Kubernetes, you can take advantage of that. You can pretty much compile the code, Dockerize it, or essentially containerize your application on your laptop. And during the deployment time, you can just deploy it into EKS. So it will be very simple deployment for you. And if you're already invested into Kubernetes technology, you can extend that framework through EKS. All right. Here is a process flow here. So basically, you will create your container images. This is where ECR comes into play, right? And you are doing the task definitions. The second step is defining your application stack, and then basically you're launching containers. In ECS, the third step where you're launching containers, you have two options, either EC2 or Fargate. The difference between the two is if you are going the EC2 deployment model, then you are responsible for making sure you are giving enough EC2 instances to ECS control, so that as your demands are scaling for the application, you will have to manually provision servers and give it to EC2 to ECS so that the computations can be forwarded to the task nodes registered with ECS. With Fargate, you don't have to worry about provisioning servers. You're still doing the same thing in terms of task definitions, but when there is more computation necessary, ECS will talk to Fargate, and Fargate will auto-provision instances based on your requirements. So that's the major difference between ECS deployment model with the EC2 or ECS deployment model with Fargate. And basically, the auto-scaling functionality, this is also extremely important. Another minute detail here, when you are scaling it at scale, with respect to ECS, when you are not only you are doing at the ALB level the traffic routing, but also you can assign IP address to a single task node, right? So the maximum you can the maximum number of ENIs is, I believe, about 12 ENIs, right? So you have a limitation there in terms of number of task nodes. In case of Kubernetes, the difference is you can have an ENI, a single ENI, mapped to multiple pods. So there could be more number of pods leveraging the same ENI, whereas on the ECS side of the house, you will have a single task node assigned to a single ENI. So I hope that makes it clear for you. But another advantage of ECS is for security-conscious customers who want to have fine-grained access control, you can assign roles to tasks, which is not possible on the EKS side. What does that mean? Why is that important? Because if your InfoSec says, I don't want you to configure, I don't want you to key in your credentials directly into the tasks, take advantage of IAM roles. So what happens in that case is the task nodes will assume role and make a service call to DynamoDB or S3 or any other AWS services. So that way, you're not actually keying in your credentials or into your application itself. A very good security model. So that's the main advantage. Just to give you an overview, so without ECS, before ECS, the top 3 boxes that you see there, the scheduling, the orchestration, the cluster management, and the placement engine, all of this was done by customers themselves. That's a very difficult step to do in terms of managing. But with ECS, again, here is a customer example. Tibco has implemented a large-scale container placement by deploying using ECS. And of course, there is also an element of Lambda here. The bottom line for this specific customer, Tibco, with this specific implementation is they reduce their server footprint by 40%. That's a lot of benefit, a very good TCO, a very good ROI, and also cut down on the deployment time. Why? How can that cut down on the deployment time? Is basically you're doing CI/CD all the time in a DevOps model. It's no longer a monolithic application where you have to take down just to make a small update, right? That's the advantage. You're more agile, and the time to market for you will be much faster versus a monolithic application running on a VM. So that's the major advantage of running containers. So EKS, like I mentioned already, it's Kubernetes managed Kubernetes control plane. The deployment model is pretty straightforward. You will provision a cluster, and then you deploy your worker nodes. Worker nodes get instructions from the EKS master nodes. Those 3 master nodes on the left side, those are the ones that the control plane that is managed by Amazon. And these 3 master nodes are, if you're familiar with Aurora, this is a similar implementation, meaning the masters are in 3 different AZs. That gives you higher resiliency when you're deploying on AWS. And here is the example architecture for EKS on how it works. You can have multiple pods running. And the advantage here is, like I mentioned, in case of EKS, you can leverage the ENI for multiple pods. So you can aggregate more pods into the same set of ENIs. All right, now switching quickly into serverless. So we reviewed EC2, we reviewed the containers, and then now it's event-driven programming. This is another massive paradigm shift in terms of developer capability to react to events on the fly without managing servers. That's a fantastic option for customers who want to take advantage of serverless programming. Quickly, again, from a deployment perspective, essentially what you're doing is you're looking for specific events. In this case, on the left side of the screen, you see upload code to AWS Lambda. You are selecting a runtime environment. These are pre-canned containers that are already created by AWS. All you are doing is to take advantage of the container environment. Behind the scenes, we are running containers for you, but all you should care about is running. It's different abstraction layer. At the end of the day, if you think about all three different compute options, the VMs are giving you abstraction from hardware. The containers are giving you abstraction from the virtual machine. And the serverless is giving you abstraction from everything below. All you care about is in terms of just executing code for a specific event. To give you, again, a lot of customers, enterprise-grade customers, are leveraging Lambda for a wide variety of use cases. And we'll give you just a quick overview on. So for example, if you take a picture and you are uploading to S3, you want to create a thumbnail as part of that process, right? As soon as you upload an object, you can trigger, again, this is what event-driven programming is all about. You can trigger a Lambda function that can to take your input file and then process that, resize, or do whatever it is that's necessary to create the intended outcome. We're doing, again, a lot of customers are doing this at scale. So if you're wondering about how do you do serverless programming at scale, Zillow has done it. They take online, order is placed, and there is a DynamoDB database that is ingesting all these order processing, and it triggers a Lambda function. Basically, it's taking all those orders that is inserted into your key value pair and key value database, and a Lambda function runs the data transformation code and loads the resultant set into a Redshift database. Why into Redshift database? To do additional analytics on top of that. Here's a use case for, this is another use case, batch processing. In this case, it's a Fannie Mae's implementation of grid computing. Just imagine you can do HPC grid computing at scale using Lambda functions. And for the folks who are not familiar with this specific workload, in this particular scenario, Fannie Mae was able to scale to up to 30,000 concurrent Lambda functions. And that's right, 30,000 Lambda functions. So the idea is massive amounts of data is ingested into data lake on S3. And based on the key space within the S3, it triggers a Lambda function, and it's doing a form of grid computing, HPC-type grid computing, and batch processing on top of this. So these are the different patterns at scale. I hope you walk away with a good understanding of VMs, containers, and serverless. I will be available in the hallway for any questions. Thank you all. I appreciate you coming to this session.